All right, we're going to look at a new type of coordinate system called the polar coordinate system, which is a system based on a fixed point, which we call the pole, and a ray that begins at the pole called the polar axis. All right, so here is my fixed point. Here's my pole. And my polar axis typically goes along what we would think of as the positive x-axis in that direction. So this is my polar axis, which we think of as like the initial side of an angle in standard position. Similar. Okay, and along the positive x-axis. And what we want to first talk about is ultimately we want to graph in our polar coordinate system, but before we can graph equations, we need to be able to graph points. So how does it work? If I have a point in my polar coordinate system, then it's going to have an ordered pair, and the first coordinate is going to be a value of r, and the second coordinate is some angle theta. Okay, and we talk about r being the directed distance. So it's not just the distance like we've talked about in the past. It's a specific direction depending upon if r is positive or negative. It's a directed distance from the pole to the point. It can be positive, it can be negative, or it can be 0. So our value of r could be any of those. Our angle theta is an angle in degrees or radians. That could also be a positive angle, a negative angle, or 0. Okay, so if r is positive, okay, then the point P lies on the terminal side of the angle theta. So if this is my angle theta, then if r is positive, point P would be here, and r would be this distance. Okay, so you find the terminal side of the angle, and you go in the that distance r from the pole, and that will give you the point. If r is negative, then you still find your angle theta, but the point lies on the ray opposite of that terminal side of that angle. So if r was negative, then I would take and find the ray opposite, and I would go that distance r in the direction on that ray opposite. So it would be this direction. Okay, so whatever your angle is, you're still locating the terminal side of that angle. You just decide if you go if the point lies on that terminal side or the ray opposite. Okay, so let's do some graphing. We're going to plot each point in the polar coordinate system. Now, these polar coordinate systems are divided up into 30-degree sections, or pi over 6. You can find them all different sizes. These in particular have a radius of 5, but there's all different kinds of varieties out there. So I have point P, so its r is 4, and my angle theta is 135 degrees. Okay, so first thing I would do is locate my angle theta, 135 degrees. So if these angles are 30-degree increments, then basically we know that halfway between 30 and 60 is 45. So if it's an angle with a 45-degree angle reference angle, then it's going to go divide kind of our quadrants in half. Okay, so I'm going to find the terminal side of my angle theta, 135 degrees. So I'm going to go, I start here on my polar axis, and I go to 135 degrees. So my terminal side would be over here. Okay, so this angle is 135 degrees. So because R is positive, then I'm going to go 4 units out from the pole. So I'm going to count 1, 2, 3, 4. So this is the point P. Okay, you don't have to show all the sides of that angle. I just do because I think it's helpful for the picture, for showing how I got there, but you don't have to, as long as you can find the location. Okay, let's plot Q. Now, see the difference? R is -4. So we're still going to locate our terminal side of our angle of 135 degrees, just as I did before. Whoops, I'm not very good at that direction. Okay. So that's 135 degrees. Now, because R is negative, we're going to go in the opposite direction. So I'm going to go on the opposite side, which means my point is going to lie out here. 4 units, or a distance of 4 from the pole. So 1, 2, 3, 4. So here is my point Q. All right, so let's graph R, 2, -30. So I find the terminal side of my angle, -30 degrees. So if I'm starting at my polar axis and I'm going in the negative direction, 30 degrees, then here is my terminal side of that angle. So if R is 2, it's positive, I'm going to go, my point lies on that terminal side 2 units from the pole. So here is my point R. And then S, -3, 630 degrees. Okay, so I need to find the terminal side of 630 degrees. We've done that before. Clearly that's more than one trip around, so we want to find the least positive coterminal angle. So if I subtract off 360, I get 270. All right, so my terminal side of the angle will be here. All right, now because R is negative, I am going to go on the ray opposite that side. Oops. So my point would be 3 units in the opposite direction, basically, out here. So I'm going to go 3. 1, 2, 3. So this is the point S. Okay, so we can graph. Now, hopefully you can see that what if I said here, when I got my coterminal angle, I'm basically plotting this point, -3, 270, aren't I? Right? So there are other points that would be located at this other polar coordinates that would land at this exact same spot. Okay, so different than our rectangular coordinates in our XY coordinate system. So in the rectangular coordinate system, if I have an ordered pair, a pair of X and Y coordinate pair, there's only one location. If I say plot the point 2, -3, well, you know you're going to go right 2 and down 3. Okay, there is no other ordered pair, the point would be there. Okay, but that's not the same with the polar coordinates. There are infinitely many ordered pairs. So we want to be able to come up with equivalent ordered pairs, polar coordinates that would have the same location. So if I have the point Q is 3, 7 pi over 6. So I'm going to plot that point. So if I start on my polar axis, and I go to 7 pi over 6, which is going to be over here. Okay. So then 3 is positive, so I'm going to go on the terminal side of that angle. Oops. Can't ever switch my colors. And I'm going to go 3 units out. So 1, 2, 3. Okay. So this is point Q. So I want to give another set of coordinates, polar coordinates, that would land at that exact same spot as Q. Okay, so if I want R to be positive, that means my ordered pair should have a 3 value. So that means I need another angle whose terminal side is here at 7 pi over 6. Well, there's infinitely many. So we're going to restrict it. That 7 pi over 6 is between 0 and 2 pi, but what if we go farther out? So between 2 pi and 4 pi means I want to go 1 trip around and then 7 pi over 6. So basically, I'm finding an angle coterminal by adding 2 pi. So 7 pi over 6 plus 2 pi is 19 pi over 6. So that, here's another pair of polar coordinates that if I plot it, I would land in the same place as my point Q. All right, so now I want my R to be still positive, so I'm looking at 3, but now I want a negative angle, means I want an angle that's negative, that's coterminal with 7 pi over 6. So we can find the negative angle by subtracting 2 pi, or subtracting 12 pi over 6. So we should end up with negative 5 pi over 6. Okay, and now if I want my R value to be negative, okay, so here's where it gets a little interesting. So that means it's negative 3. So basically, I need an angle on the ray opposite this ray at 7 pi over 6, which means I need an angle over here on this ray, okay, that terminates there. So we're asking, there's infinitely many angles that are coterminal here, but we're asking for one between 0 and 2 pi. So if we're just talking 1 trip around, a positive angle, that's going to be pi over 6, which is basically the reference angle of 7 pi over 6. So I could say pi over 6, I could give another angle that's between 2 pi and 4 pi. So there's infinitely many polar coordinates that have the same point. Okay, here's one for you to try. So pause the video and see if you can come up with these other polar coordinates, but here we're talking degrees. Okay, let's see how you did. So point P lies in what we would call quadrant 4. So let's give some other ordered pairs here. So if R is negative, then it would still be negative 5, but we want an angle between 360 and 720, so 480 degrees. All right, here R is negative, once again negative 5, and then a negative angle between 0 and negative 360 would be negative 240. And if R is positive, it would be 5, and I want a negative angle between 0 and negative 360, which would be negative 60 degrees. Okay, so basically, we want to be able to convert between rectangular coordinates and polar coordinates, okay? We know rectangular coordinates, x and y, in our xy coordinate system, okay? And then we have polar coordinates where we have our r and our theta. So let's think about it for a second. If I have x and y, if I have a rectangular ordered pair with x and y, I want to convert it to r and theta. So that means I need r and I need theta. Okay, so if I think about here, if I can think about this being r, all right, so this distance is x, this distance is y, so I can see the relationship here between x, y, and r. It's basically Pythagorean theorem or distance formula, so to speak. So x squared plus y squared is equal to r squared. Okay, so if we know x and y, we can definitely find r. We could simplify that also and just say r is the square root of x squared plus y squared. All right, now we need this angle theta, right? So in order to find theta, what do we know? Well, we know that if we have x and y, we know that the tangent of theta is y over x, which then if I had to use my calculator especially, I know that I would use the inverse tangent of y over x, and we know that x cannot be 0 because tangent is not defined when x is 0. Okay, so here's some relationship, how we can use x and y to find r and theta. Okay, now what if I have the polar form? I have r and theta and I want x and y. So think about what we know here. I know that this distance is x and this distance is y. So we've talked about this before. We know that the cosine of theta is x over r, and the sine of theta is y over r. So we're looking for x and y. All right, so if I solve this for x, I get x equals r cosine theta. So to find my x value, I take r times the cosine of that angle. And to find y, I take r times the sine of my angle theta. Okay, so these are some relationships here that we're going to use to convert between rectangular and polar coordinates and ultimately rectangular and polar equations. Okay, so these will be good things to keep handy. So here's just a nice example. If I have the rectangular coordinates 3, 3, okay, what would their equivalent coordinates be in the polar coordinate system? So you can see that they're located in the same place. This would be my r, 3 square roots of 2, and my theta would be pi over 4. Okay, because I know this is pi over 4 or 45 degrees, which remember when I have a triangle here, if this is 3 and this is 3, I know this is an isosceles right triangle, so this is 45 degrees or pi over 4. Okay, all right, so how do we go back and forth? All right, so I want to take this ordered pair, or this pair of polar coordinates. Okay, so this is polar form, and I want to convert it to rectangular form. So if I'm going from polar to rectangular, I need x and y. All right, so here's my relationship. So to find x, I take r times the cosine of theta. So I know that r is -5 and theta is negative pi over 4. Okay, and yes, you must use that angle. You must keep that sign. Okay, so my x coordinate is -5 times the cosine of negative pi over 4. Okay, so I'm going to take -5 times the cosine of negative pi over 4. Cosine's positive in quadrant 4, so it's going to be square root of 2 over 2. So the x-coordinate of my point that would be in the same equivalent in the other coordinate system would be negative 5 square root of 2 over 2. My y-coordinate of the point would be negative 5 times the sine of negative pi over 4. So that's negative 5. In quadrant 4, sine is negative, so that's negative square root of 2 over 2, which comes out to be 5 square roots of 2 over 2. Okay, so we're saying then that this ordered pair in polar would be equivalent to negative 5 square roots of 2 over 2, 5 square roots of 2 over 2 in rectangular form. Okay, now I like to see them side by side. So one thing I would do if I was going to graph this, I'd want a decimal approximation for those points. And I know that 5 square roots of 2 over 2 is approximately negative 3.5. So it's negative 3.5, positive 3.5. So I know this is going to be in quadrant 2. Okay, so let's take a look at those together. And maybe not. I don't have a grid. It's lost. Well, darn it. It was worth a try. Okay. Anyway, you could graph those and see that they were in the same location. All right, let's go the other direction. Here I have rectangular coordinates. I need polar, which means I need r and I need theta. Okay, now plot the rectangular coordinates. We can do that. We know it's going to be in quadrant 1, right? Because both of those are positive. If you want a quick visual, it's not necessary, but I'd have to get, once again, I'd have to get a decimal approximation for those values. So the approximate would be square root of 6 over 2 is approximately 1.2, and square root of 2 over 2 is approximately 0.7. So if I was going to graph them, I'd be going to the right 1.2, and I'd be going up 0.7. So looks like it's going to be somewhere right in here. Okay, so it's going to be in quadrant 1. Okay, so let's convert. Now, to me, I think this is trickier of the two. This is my x, this is my y. So here's what I've got over here. I need r, which is the distance that it is from the pole in the polar coordinate system. So you can either find r here or here. Okay, this is probably the faster, right, to go straight to here. X squared plus y squared. So my x coordinate is square root of 6 over 2. I'm going to square that. My y coordinate, I'm going to square that. And then I'm going to add them up and take the square root. So when I square this, I get 6 over 4. And square here, I get 2 over 4, which leaves me with 8 over 4, which is the square root of 2. So r is the square root of 2, meaning if I graphed it in the polar system, the distance here, this distance r, would be square root of 2. Okay, which it's there too, but Okay, so now what do I need? Now I need theta. Okay, so to find theta, we'll use x and y, basically similar to what we do in complex numbers. We're going to find the tangent of theta and then figure out what theta is. I know it's quadrant 1, so I'm going to get right to it with my reference angle. So I know that tangent of theta, this angle here, is y over x. So it's square root of 2 over 2 over square root of 6 over 2. So basically we just need to simplify that and figure out what the angle is. Whoops, what did I do? That was bad. Yeah, let me fix that. Square root of 2 over 2 over square root of 6 over 2. Okay, so that simplifies down to square root of 2 over square root of 6. If I rationalize, I get square root of 12 over 6. And we always simplify our radicals, so we should simplify square root of 12 as 4 times 3, so that's 2 square roots of 3 over 6, and reduce. Ooh, got some serious simplifying here. This reduces down, so I end up with the tangent being square root of 3 over 2. Oh, no, I'm sorry. Square root of 3 over 3. That's not a tangent value. If we're talking unit circle anyway, or thinking unit circle. Okay, so I'm looking for an angle in quadrant 1, right? Quadrant 1, whose tangent is square root of 3 over 3. So that's telling me then that theta is, if tangent square root of 3 over 3, we're talking pi over 6 or 30 degrees. Okay, so this point here in rectangular form would be equivalent to square root of 2, 30 in rectangular form, or polar form, I'm sorry. All right. So then you can find other pairs equivalent to that by just adding and getting coterminal angles. So that's just something we've already done. Okay, now here's what we really want to do. We want to graph these polar equations, okay? Remember, polar equations involve r and theta, okay? So here's a very, 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 very basic polar equation, r equals 3. Okay, so let's think about what that means in terms of my polar coordinate system. It's very similar to something we've done in algebra where we have x equals 3 or y equals 3, something like that. We only have one of our variables. We know it's a special type of line, okay? And this is very similar here, that we're saying r is always 3, meaning that all of the points on the graph of this equation have an r value of 3, but theta can be any angle. Okay, so any angle I choose for theta on the terminal side, if I go 3 units out, I have a point on the graph. So if I start here at 0 degrees or radians, it doesn't matter, then I have the point that's 3 units out. If I go to 30 degrees or pi over 6, 3 units out. So no matter what my angle is, I'm always a distance of 3 from the pole. So we can see that ultimately if we plotted every point for every angle, we would have a circle. Okay, so the polar equation r equals 3 is a circle and centered at basically at the pole here, but it's a circle, I should say, of radius 3. Okay, now what we know, we should know what the equation of a circle of radius 3 centered at the origin, what its equation looks like, but let's pretend like we don't. And how would we convert that to a rectangular equation? Rectangular equation, remember, we need x and we need y. Okay, so I need an equation involving x and y. So think about what you have for your equations. You know that r is the square root of x squared plus y squared. And you know that, oh, or you could use, you know that x squared plus y squared is r squared. Well, I want to get rid of r and have x and y, so this seems like a good choice. All right, so if I replace r with the square root of x squared plus y squared equals 3. Okay, I don't know why that pen shows up. So let's pretty that up a bit. Let's square both sides, which would give me x squared plus y squared equals 3 squared, or 9. So this equation in polar form is equivalent to this equation in rectangular form. And hopefully you recall this about circles. This is a circle. Center is at the origin, and the radius is, remember, this is the radius squared, so radius is 3. So if we want to talk in general, we could say, oh my gosh, that pen, I don't know how I got that, but it is driving me nuts. Maybe I pushed, I don't know why. So in general, if I have x squared plus y squared is equal to a squared, some number a, then that's rectangular form. Polar form would be r equals a, or technically it could be negative a, couldn't it? Because whatever I square to get that value. So it's plus or minus a. So here, if I took 3 and squared it, I would get 9. All right, so a circle in polar form is just r equals a positive or a negative number. Pretty cool. Okay, now, oh, this is fun. All right, so look at this equation, 4 cosine theta. We have no idea what it looks like. We've never graphed one. So back to when you learned how to graph in algebra, you plotted points, okay? Well, here, my independent variable is theta, meaning I choose theta, I find r. Okay, so let's just do a little plug and chug. We're not going to do a whole bunch because you're going to see it's really tedious, actually. So we want to talk about what's a better way of doing this. Okay, so if theta is 0, now let's go. We're in radian mode. If you use your calculator, it's totally fine, but we can do it without using the trig buttons on our calculator. So I'm going to say then that r here is 4 times the cosine of 0. Well, the cosine of 0 is 1, so 4 times 1 is 4. Okay, now if you're going to graph that, you don't have to write the ordered pair, but technically the ordered pair is r theta. Okay, so if we're going to graph that, that is the point 4, 0. So I'm on an angle of 0, which is pretty sweet. You can just start with the angle and then go for a distance. I'm on my angle of 0. My terminal side is here, and I'm 4 out. 1, 2, 3, 4. Okay, there's my first point. All right, so here, if I say theta is pi over 6, 4 times the cosine of pi over 6. Well, what's the cosine of pi over 6? Square root of 3 over 2. So I get 2 square roots of 3, which we probably want a decimal because that's our r value. So that decimal is approximately, sorry, this is a little tight, 3.5. So I'm going to pi over 6 and I'm going out 3.5. 1, 2, 3.5. There's another point. Okay. pi over 4. What's the cosine of pi over 4? Square root of 2 over 2. So 4 times the square root of 2 over 2 is 2 square roots of 2, or approximately 2.8. So at pi over 4, which I don't have on here, because this is a 30 sector, so I know it's got to be right here in the middle. Whoops, come on. Here's pi over 4. All right, and I'm going to go out about 2.8. 1, 2, 3, so about here. Now, mine's not drawn so great. That looks pretty sad, but, you know, we can only do so much. Okay, so pi over 3. Cosine of pi over 3 is 1/2. 4 times 1/2 is 2. So at pi over 3, I'm out 2. Pi over 2. Cosine of pi over 2 is 0. 4 times 0 is, whoopsie, 0. So at pi over 2, I'm at 0, which means I'm at the pole. Ooh, that looks really bad. Something doesn't seem right. 1, 2.8. Pi over 3 is 2. I don't know. It must be my 0.8 that looks bad. All right. Well, anyway, makes me sad that I can't draw. I think it's this one that looks out of place, but I was hoping you could see it. And maybe this one's a little large. So can you see how this is really tedious? All right. That's my point. Okay, what happens at 2 pi over 3? Well, at 2 pi over 3, cosine is negative. So these two have the same value, except this one is going to be negative. So if I go to 2 pi over 3, I'm on the ray opposite. So at 2 pi over 3, I'm going to go the opposite direction out 2. Okay, so we can see here, this point has a positive value. This one has a negative value. Okay, so where are we going? 3 pi over 4. So it's going to be 2.8, but it's going to be negative 2.8. So if I go to 3 pi over 4, I go opposite. I'm somewhere over here. So I'm going to just do my reflection of this point to help me. All right, and 5 pi over 6 is going to be 3.5, but negative. So at 5 pi over 6, I'm over here at the negative. All right, and then back to pi, we're back to here. So I don't know if you can tell what this is. That's the whole point, that it's pretty tricky. But it is actually a circle. Okay, so it's a circle. What's its radius? Okay, so I know that this distance is 4. All right, so the center would be here at 2. So it looks like its radius is 2. So it's a circle. And it looks like the center is at 2, 0. And the radius is 2. Okay, now, if you felt like that was painful, it is. And that's the whole idea, is graphing polar equations by just choosing angles is tedious and time-consuming and can take forever. So when you really get into graphing these things, you're going to learn shortcuts, just like we learned shortcuts for graphing algebra functions and trig functions. Okay, but for us, we're going to say, well, wait a second. What if I convert that to a rectangular equation and then graph it? Because I know it's going to have the same graph. Okay, so let's convert to rectangular. All right, which means if I'm going from polar to rectangular, I need x's and y's. So here's the idea. I need to look for a situation where I have r cosine theta or r sine theta, and I can replace those with x and y. So I don't see I don't see here. This looks really close to me, but there is no R. Okay, so I'm missing that R there. Well, I could put an R there if I multiply both sides by R. So let's do that. If I multiply the left side by R and the right side by R, I get this equation. That's totally legal, right? I did the same thing on both sides. All right, and then I actually have another relationship here. I know that x squared plus y squared is equal to r squared. Okay, so I can use that relationship between x, y, and r. So I'm not restricted just to those two. That's more when we're converting coordinates. When we're doing equations, we can use all of them. Okay, so on the left, then, I can replace this with x squared plus y squared. And on the right, I can replace this with x, with 4x. Now, hopefully you recognize that when I have an x squared and a y squared, they're both positive with the same coefficients. It's a circle. And because I have this x terms, means it's a circle that's been shifted. So if you remember this from college algebra. So in order to put it in standard form where we can see the center and the radius, or what they call radius, center radius form, I would have to put everything on one side equal to 0. Okay, this is a fine equation. You know, I could leave it like that, but if I wanted to graph it, let's say I wanted to convert this to rectangular form and graph it, well, to graph a circle, I need the center and the radius. So this is going to require completing the square, which this is really awesome that we're reviewing this now, because down the road, we're going to see conic sections again, and we're going to hope that you remember this. So it's a nice review. All right, so remember, completing the square. I need to add something here to make a perfect square trinomial, and then I need to turn around and add it. Come on, add it to the other side. All right, so what do? We take half of this, so half of 4 is 2, and we square it. 2 squared is 4. Okay, then I add 4 to the other side. So I factor that perfect square trinomial. And now I have what's called center radius form. And if you recall, that standard form for a circle is x minus h squared plus y minus k squared is r squared, where the center is hk, and of course the radius is r. So this is user-friendly because it jumps out at us. So I can see here that my center is, this is my h. So h is 2 and k is 0. So my center is 2, 0, and my radius is the square root of 4 or 2. Okay, so ultimately what we'd like you to do now, we're trying to get the point across here, is don't plug and chug. Don't choose thetas and plug them in and find r's and plot that way. Convert the equation to rectangular form and use your algebra to graph it. Okay? So this equation here would have the same graph that we just did. Okay, so same idea here. I don't want to graph this. Can you imagine making a table of values and choosing theta and plugging them into that and getting the r's and plotting? Ugh, I don't want to do that. So what we're going to do is we're going to convert it to rectangular form and see if it's a rectangular equation that we know how to graph. We know how to graph a lot of stuff in rectangular or x and y's, so we're good. All right, so what do we want to do? I want to get rid of the fraction on the bottom. So I don't want this in the bottom, so I'm going to multiply both sides. So I'm going to take and multiply by 2 cosine theta plus sine theta on both sides. So when I do it on the left, I have r times that, and on the right, it would cancel out. So I'd end up with 4. Okay. Now, I'm going to go ahead and distribute that. So I get 2r cosine theta plus r sine theta equals 4. Okay, now what am I trying to get? I need to get rid of r's and thetas. I need x's and y's. Well, here's that nice little conversion. R cosine theta is x. R sine theta is y. So I can do that replacement. Ooh, look at that. Here is a rectangular equation. Do you know what that graph looks like in my rectangular coordinate system? I hope so. It is a line. How you graph lines is up to you. In this standard form, ax plus by equals c, you can just get the intercepts. So if y is 0, x is 2, so it's on the intersects the x-axis at 2. If x is 0, remember I can cover this one up, pretend like it's not there, y equals 4. So my y-intercept is 4. To me, that's the fast way in that form. So here's my line. Whoops, not the greatest. Okay, if you didn't like that, you could always switch that to slope-intercept form. Oops, I don't want to do that there. Sorry, I want to keep this. Hold on a second. Let me go over here. So you could write it as slope-intercept form, y equals negative 2x plus 4, and use the y-intercept in the slope. Okay, so this is my line in rectangular form. That exact same line, meaning this equation here, would have the exact same graph in my polar grid. So I can use kind of those intercepts to help me. Here's this point and this point. Okay. So here's the polar equation for that line. Here's what I want you to see. This is the cool aha moment. I want to hear you oohing and ahhing at home or wherever you might be. And this is the equation in rectangular form, but I want you to see it in this version actually. So 2x plus y equals 4. Okay. Do you see a relationship here? Here's the 4, here's the 2, and here's the 1 here. Okay, so in general, here's what we can say. Equations, if they're in rectangular form and standard form, ax plus by equals c, will convert to a polar equation of r equals c over a cosine theta plus b sine theta. Okay, so that's sort of cool. So anytime you see a polar equation in this form where you have cosine plus sine in the bottom and a number on top, it's going to be a line. So as we've seen so far, every one of our polar equations is solved for r. Okay, so that's one thing to keep in mind. Okay, let's do one more fun one and then we're done. All right, last one. Convert this polar equation to a rectangular equation and then graph it. Okay, all right. So, secant. I don't have anything with secant, but I can rewrite secant as 1 over cosine. So I basically have 2 times 1 over cosine, which is 2 over cosine theta. All right. Now it's looking a lot better. I've got cosine and r. But once again, get rid of the fraction. So I have r cosine theta is equal to 2. Ooh. R cosine theta is equal to x. So the rectangular equation is x equals 2, which is a vertical line. Okay, so here's the graph in both polar and rectangular. okay? So in polar, it's 2 secant theta. It is a vertical line crossing the polar axis there at 2, and it's a vertical line crossing the x-axis at 2. Now, so we just see pretty basic stuff in this class. We do circles and lines. If you're going to go down the road, unfortunately, we don't have the time to do it in pre-calc, but we do it in Calc 2. So if you get to Calc 2, you'll get to graph really cool looking things, circles, spirals, limacons, which is French for snail, limacon. And there's different ones depending if it has the inner loop, if it's a cardioid, if it has the dimple, or if it's convex, it's more like, looks like a circle. But I just have to point this out. This is one of my favorites, and a student actually said this. This cardioid could also be called a gluteoid. My favorite. And what does this graph look like? Infinity, which is a lemniscate. Infinity, how do you spell that? E? No, Y. Oh my gosh, what happened? Probably because it's late. All right, anyway, you can see, look here, we graphed r cosine theta is a circle. RA sine theta is also a circle, so the sine and cosine tells me if it's shifted left, right, or up, down. So there's lots of things that you would, if you continue on, you'd learn what does A and B tell you to do and what's the graph going to look like. So, end on that fun note. Thanks for stopping by, and I hope this helps.